Hi, my name is Christopher Grattoni. I'm a high school mathematics teacher at Wolfram High School in Palatine, Illinois. And my talk today will be co-presented with some of my former students, and we'll be talking about using Wolfram demonstrations in a high school classroom as a capstone project for seniors. Hi, thanks everybody for being here today. My name is Chris Grattoni. I'm a high school teacher at Wolfram High School in Palatine, Illinois. And we're going to be talking about Wolfram demonstrations. And this is a capstone project that we do at Fremd High School with our multivariable calculus students. And I have some special guests with me today. I have some former Fremd graduates who have created this project in the past. So we have Robert Andrews. We have Danny Johnson. I don't want to block you, Kevin. We have Kevin Kraut. And then we have Matt Nicholson, Roshan Rajan, and Berwin Shi. And so they'll talk a little bit about the projects they created, what they're up to now in their educational life, and what sort of impact the project had for them. But first, I thought I'd give you guys a little bit of background about the project itself. So this is an excerpt from the project description that I hand out to all of the students. It's at the end of the year after AP testing. So the students will finish their final exam for the Calc 3 course that they're taking. And then we usually have about 3 to 4 weeks at the end of the school year after that final exam has taken place. There's AP testing, and then there's a couple weeks at the end of the school year after that. And so their task is to create a Wolfram demo that basically highlights an interesting mathematical or scientific or just otherwise interesting idea that they're passionate about or interested in. And I'm guessing that most of you have seen the Wolfram demonstrations project before, but if not, Berwin, do you want to just show really quickly? It would be just in the web browser. I had pulled it up. I didn't know if we were going to have internet or not, so I haven't had it ready, but I wasn't planning on necessarily using it. So of those 10,922 published projects, about 30 of them have been published by Fremd High School students. And there's all sorts of different topics that they have created for those. Yeah, you can. That's great, Berwin. Yeah. That's right. Let's go back to the slideshow then. We don't want to wait for it. Oh, okay, it came up. So there's 27 of them listed there, and then some students forget to put Fremd High School in their description, so they don't come up when you search them. So there's a few more than those 27. And you can see all sorts of different subjects, and I kind of classified later on in the presentation what subjects they picked. But so the main thing that I try to communicate to the students, if you do try a project like this in your own classroom, is I tell them to try not to be overly ambitious with the scope of their project, because some students try to take on the world and make this huge project, this really complicated demo that they're not going to finish in 3 weeks. And so we try to keep them small and interesting and to the point. And the main thing is that the demonstration should help the user learn more about the subject that they're interested in through interactivity. So that's the main goal of it. And it doesn't have to be Calc 3. Some students will make a Calc 3 project. Most students pick something else that they're just passionate about. Berwin, we can keep moving. A little bit about Fremd High School and some contextual information about our students. So like I said, it's a capstone project for Calc 3 students. And at this point, they have just finished a multivariable calculus, a Calc 3 course through the University of Illinois, their NetMath program. We're part of the partner high school program with the University of Illinois, and so once they have finished that full curriculum, they're kind of ready to take on a project like this. At this point in the year, the students are comfortable with plotting things in Mathematica. They're comfortable with solving interesting problems in Mathematica. They're comfortable with spherical and cylindrical coordinate systems. They know how to show multiple graphics objects in one plot, and they do know how to make simple manipulates. They do know how to make a graph and drag a slider and somehow change that graph in some interesting way. So they do have a background that has them prepared for a project like this. Berwin, I think we can keep going. And one thing that I've learned from numerous years of doing a project like this is that you need to lay the groundwork early. The first year that I did this project, I just threw it at the students at the end of the year, and it was still fun, and they had a good time with it. But only one project got published, and it was because all at once, I was asking a lot of those students. And so what we started to do over the years is build up to what this is. So Berwin, if you want to expand tip number 1. I try to assign projects throughout the year that encourage creativity throughout the entire school year. And it could be as small as an art project. This is actually built into the University of Illinois Net Math curriculum, so this isn't something that I invented myself, but it's something that I make a big deal out of in class and the students really get into. We do a spherical and cylindrical coordinate art contest. So Byrne, if you want to expand that. So this happens about halfway through the school year. That picture right there are those are all images that students have made themselves completely in Mathematica. Those are all, so it's not like they were dragging and dropping anything, and it's not like those are graphics primitives even. Those are all cylindrical and spherical coordinates. And it's kind of hard to see, but even that BB-8, I don't want to expand the code for the BB-8 because it might crash the project. There's a ton of it, but every little detail on that droid is actually a spherical coordinate plot. And if you scroll down, we can see a couple of those a little bit closer. So there's a Mickey Mouse that a student made last year. That was one of our big winners. There's Cloud City. And then there's BB-8. Berwin, I'm curious, can we rotate BB-8 at all? Because I think from all angles, he's pretty cool. Or is it an image? Darn. OK. And if you are curious, if you download this presentation, all of the code is there in a hidden cell, so you can expand it and see for yourself. And I do have some other fun little things that have happened in class over the years, and 2 of the students involved are here today. So Kevin, you can go first.
Yeah, I had to think of an idea in order to ask a girl to prom, and I thought, what nerdier and more fun way than to use Mathematica to ask a girl to prom. So I got Mr. Grattoni's help to set up under the guise of helping everyone with their end of the year project, and just made a brief slider that drew some cylinders asking a girl to prom with me. So it was really fun. And
she did say yes.
She did.
Yeah.
I also created one.
This is a couple years later.
Yes.
And independent of Kevin. You didn't even know that Kevin had done that, if I recall. But
yeah, I was also asking someone to prom, and I thought it would be a fun little thing because they were also taking the same class with me through the Net Math program. So that semester I was taking differential equations. So I wanted to do something a little bit more focused around that. So I used one of the topics, which was Fourier transforms. So I had a bunch of these images, which I did in Edge, translate based on Michael Trott's code. He has a parameterized version of certain images. So I kind of extracted kind of the creative parts that I wanted to use, and then added my own version to kind of come up with this giant grid of different images that I got coalesced to the proposal.
And for me particularly, that was the work that you did, Roshan. I was really excited about that because you took a blog post that someone at Wolfram had written. You read it, you understood it, and then you incorporated it and learned what was in there. So that was, as a teacher, that was a very awesome moment for me. So. And then the other tip that I have is if you do try a project like this in your own classroom is to mention the project early and often. The sooner that the students know that they're going to make something like that, the sooner the gears are turning and that they're thinking about what they could create. And honestly, at this point, after doing the project for since 2012, at this point, usually when we get to the project stage of things, the students already pretty much know what they want to make. They'll have seen something in physics. They're like, oh, I can make a demo of that. Or they'll see something in a Wolfram blog post and say, oh, I could take that idea and go in this direction with it. Which helps a lot because then they're not spinning their wheels for the first week of the project just trying to think of what they're going to create. It also sets the expectations high because early in the year I will show them what previous students have made, and they always want to raise the bar. They want to do better than last year. And so if you show them what was published in the past, and I think that has happened year after year where more and more projects have gotten published and the complexity of those projects has continued to increase. And the other thing I'll do is post newspaper articles about interesting things in the math world, interesting things in the physics world that students would be ready to understand. And sometimes that sparks nice ideas. And creating contests, the art contest, obviously. They get very, very excited for that around February, and that starts the spirit of competition, so that later in the year when we make the demos, they really want to create something neat. So thank you, Berwin. Let's see what else. Is there anything else in there? No, we're good. In terms of picking project ideas, I let them go in any direction that they want to. It's more about creating something that they have a vision for and that they're interested in, rather than it having to be about the curriculum from the course. Now, as they start creating, it does end up that they learn how to plot things in spherical coordinates. They learn how to plot in cylindrical coordinates. They learn some optimization. A lot of that actually does come in. So they don't expect it ahead of time, but they end up doing calculus for these projects anyway for the most part. So it makes me happy. But I went through old projects and figured out these are very approximate ratios of the different subject areas, but physics seems to be the big one. It's sad for me, but mathematics always takes second place to physics for these projects. And then we do get a lot of biology, chemistry, computer science, and then fractals. Every year there's a billiards project. Every year someone wants to really recreate billiards in Mathematica, and sometimes it goes better than other years. Epidemiology, especially when the Zika virus was it's still the hot thing to talk about, but when that was really big news at the time, a lot of students were very interested in epidemiology. We have a zombie project even with epidemiology. Okay, Berwin, let's keep going. He's telling me to go, so we're gonna keep moving. And I'm gonna wrap up soon, but in terms of picking project ideas, the ideas that I suggest usually are last place. Sometimes a student will see a project that I suggest and be like, oh yeah, I'll do that. Usually it's something that they saw in a different class, a difficult problem from physics, for example, that they're like, oh, I can make a demo of this. A student hobby or interest is big. Or sometimes just browsing the Wolfram demonstrations project and looking at what other people have created. Sometimes they'll see a neat project that someone else has come up with, and they'll say, oh, I could use this same idea, but in this direction, or I could take this physics idea and turn it into this project that's similar, but not exactly the same. So, all right, Berwin. And then I'll make this quick, but at the beginning of the demonstration project, the first few days, I do spend some time helping them learn how to use Mathematica in a way that they're not used to, because they had spent an entire school year learning how to use Mathematica to solve calculus problems. And I need to transition them to learning how to use Mathematica to create an interactive demo using Manipulate. So there's things that we don't talk about earlier in the year, local versus global variables, showing multiple graphics outputs all in one plot in a very precise way. So there's some of those things. If you expand that, Berwin. Is it just taking a long time? Yes. Yeah. I'm not going to spend very long on that, but this is something that we create in class. We start with a really simple, their first demo with a sign plot, and then we just keep adding more and more to it. And this takes about a class period. And by the end of that class period, they have a code base that they can refer to just as basically a template for putting their project into. So they learn how to move around controls. A lot of this is from the Wolfram Introduction to Manipulate article. So they can learn the same thing from that article, but this is kind of scaffolding it and adding in these features, a little bit at a time until there's certain things they need to know how to do. They have to be able to label controls. They need to know how to put labels into their plots. And by the end of the period, they have a pretty neat little demo that they can use as a template. All right. And then the main thing that I want to communicate is that adopting a NetMath style philosophy in your classroom does help with getting great results out of students. So what I've learned over the years, and at first I was uncomfortable with this idea, but after several years of teaching this way, it became, now I can't imagine going back. But just really believing that students can and will do amazing things when you give them freedom to experiment, when you give them open-ended problems, when you give them a chance to express themselves, pursue their interests. The great thing about the NetMath program is there are problems that the students can just, if they're not interested in it, they can solve it, they can give their explanation, and they can move on. And that problem might not be meaningful for them, but they learned something. And then there's other problems that they might see that they are really interested in, and it's something that they want to explore more. And it's a sandbox, so they can keep writing and they can keep putting more code in and make that problem their own. And once the student has that mindset, they can continue that when they jump into a project like this. All right, and now Time to showcase a few of my famed former students. Robert.
All right. So as it says on the slide, my name is Robert Andrews. I'm a senior at the University of Illinois here in Champaign. I study math and computer science. And in terms of, I guess, the impact this project had, I think it's really interesting to look at visualizations of concepts that don't necessarily lend themselves well to some sort of visualization or intuition when you first read about them. In particular, in what I do with computer science, I'm rather interested in the theoretical side of things, looking at algorithms, things like that, and I actually help teach one of the algorithms courses here at the university. One of the things I find interesting is there are a host of algorithms, in particular algorithms on graphs, where if you just read a formal description of it, sure, a student can maybe understand it, but there's a lot of intuition from seeing how the thing plays out. And so I think, having experience with that is really useful. In terms of my demonstration, when I was back in high school, I was particularly interested in looking at conic sections and how the formulas actually mapped out to the geometry of the curves. So what I did is just wrote up a little demonstration where you can, pick your favorite conic section. It's really slow. I did not try to optimize this thing, but you can move it around a little bit, adjust some of the parameters of the curve. Oh boy. I won't play around with it too much. There you go. Sure, you can adjust some of the parameters of the curve, show different interesting parts of the curve, things like that. And then it shows how the equation for the curve changes as you move it around. And in particular, I was interested in looking at how you can rotate conics in the plane and how that influences the equation for it, and you get this xy term that shows up. As a student, I could read about this in a book and see, okay, this is where the rotation comes from, blah, 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 blah. But actually seeing how that changed as I manipulated the thing, I just thought that was really interesting and gave me a somewhat better intuition of how these things work. So that's my demo.
And Robert, just to interrupt you, the part that I was excited about this project is we learned how to do all of this with ellipses and circles parametrically in the Calc 3 course. And I like that you had that opportunity to build upon that, and those are all XY equations. So having that connection there was exciting for me, on my end at least.
Hi, I'm Dan Johnson. I'm a junior at the University of Illinois at Urbana-Champaign, and I study computer science and engineering physics, as well as a minor in mathematics. My project was a physics project. It was involving Ampere's law, which is one of Maxwell's 4 electromagnetic equations. And it relates magnetic field to current density and changing electric field. But if we consider the steady state, then it's really just comparing current density and magnetic field. So kind of what was involved in this project was showing the magnetic field given a infinitely long wire with uniform current density. And uniform meaning that it doesn't vary, the current density doesn't vary throughout the position of the wire. So in this example, you have a cylinder in the middle, which kind of, that's the wire itself. And then you have what's called an Amperian loop. And that Amperian loop is where we measure the magnetic field. It's kind of hard to see here, but those are a bunch of magnetic field vectors, or what I attempted to demonstrate. And it's cylindrically symmetric because an infinitely long wire is symmetric. And there's a few interesting aspects. You can see that if you increase the distance, the measurement distance, so the radius of the Amperian loop, then you're going to have a 1/r dependency. So as we increase this, you can see the magnetic field strength at the bottom, so it's going to go down as you increase the measurement point. But what's interesting is if you have a larger wire, or a wire of larger radius, and you increase the, wait for that for a second, you increase the measurement distance, the Amperian loop, as it increases, is going to encapsulate more and more of the current. So it's actually going to have it's going to be the magnetic field is going to be proportional to the radius of the Amperian loop as it increases throughout the wire. But then once you get outside of the wire, it's going to have that 1/r dependency that we saw before. And then another quick example of how this works is it's a right-hand rule. So if you flip the current around, then it's going to flip the other way, just like it's going to be in the negative phi hat direction instead of the positive phi hat direction. And how this demonstration is kind of related to what I do now is I'm currently working on a fusion device on campus at the University of Illinois where we magnetically confine a plasma. And so we have a ton of different magnets. We have toroidal magnets that create a toroidal magnetic field. We have helical magnets. We have vertical magnets. And we also have the plasma itself constitutes a current. So that plasma creates a plasma current, which is going to create its own magnetic field. So we have to account for all these different factors and a superposition of all these magnetic fields to actually determine the magnetic structure of the system to confine the plasma. So that's kind of how it relates to what I do now. And that is what I have.
Hey everyone, I'm Kevin. I was a 2013 Frem grad, and I'm now a senior at Northwestern, getting my bachelor's and master's in mechanical engineering with a concentration in fluid dynamics. I plan on working post-graduation, and after working for a couple years in the industry, I want to see if further schooling is for me or not. So the impact this project had on me, like I honestly have nothing but good things to say about this. Both as a high school senior, it was a really great thing for me because it was post-AP tests, all that stress that was built up I could release by like putting my energy into making this project really great. And then it also helped me, it gave me an environment where I had no restrictions or few restrictions on what I could do, and I really got to explore like what it was to code or make a demonstration that was my own, which proved to be really helpful as an incoming engineering student at Northwestern, because I was immediately introduced to MATLAB, which is what Northwestern engineers use all the time, and it was super easy to pick up, and I really attribute that to the experience I had with this project, because I just learned the skill set that I needed to succeed in programming thanks to the work that I did with this. And I've used MATLAB ever since then in a variety of like high-level engineering classes and research projects. Most recently, I've been working in the Northwestern Neuroscience and Robotics Lab and doing a lot of analyzing data using programming, and I really think this was a huge experience for me that I really liked. I will explain my project after Berwin talks, since we worked on this together. So.
All right, cool. So I'm Sperwin. I'm a senior in computer science at the U of I. A lot of my interests are with data, and this project turned out to be like a really good introduction to taking data, in this case like music notes, and manipulating that in some way. On campus, I'm part of ACM in this one group called SIG Music, and a lot of the stuff that we do is we take all sorts of information, be it like interactive data, like using a Microsoft Connect or all different sorts of controllers, and taking that data and making music out of it. And that's kind of similar to what we did here in our senior Capstone project. And on campus, we've created these projects for Engineering Open House, which every March we invite all middle schoolers and high schoolers from around the area to try and get them involved in engineering, show them what you can do with technology. And I feel like music is one of those things that everyone can sort of understand. It's like one of those universal languages that even if you don't understand English, you can kind of listen to music and understand and appreciate it. So that's sort of like this whole project thing that it was, this whole thing, Capstone, was an introduction for me to take an idea and implement it in some way. And that's definitely helped me through my career with creating all these projects in clubs. I'm also part of Women in Computer Science organization on our campus, and I run the tech team, which is basically leading and helping women in the organization create projects and get them more involved and not let them get discouraged throughout all the process of being a computer science student on campus. So I guess we can demo our thing now.
So the way this project came about actually was we're both musicians, so we obviously gravitated towards the note producing capabilities of Mathematica, and we started out by actually making a version of Macklemore's song "Thrift Shop," and we were like tinkering with the different notes in it or the semitones of the scales, and that's how we came up with the idea of varying a bunch of musical attributes of some famous songs to create a demonstration.
Hopefully it works.
Yeah, when you press play, it takes about 6 seconds or so to kind of have to give it time to load, I noticed.
Can I press it again?
You're the computer scientist, I don't know. It might not have been a wise design decision on my end to put lots of demos all into one notebook. Berwin!
Let's see if we have the patience. All right, attempt 2. Whatever. So if it doesn't work,
You're gonna have to not maximize it, yeah.
well, okay, we can change it. It just wouldn't play. I guess. It looks like it's executing. So I guess it would just, so you can see the visual of the notes, and we can change these variables like the mode. There's a couple different ones. We have different songs that we put in, and they had to be like non-copyright. And we have plenty of instruments that are all built into the Wolfram language. And if it were,
Berwin, give it 1 minute there. So it was loading from the Wolfram research server.
okay.
So it probably, yeah, it might work in a couple seconds. Yeah, let's try again. Let's press play. If not, we can move on. We could always come back during the Q&A, and it might just start playing music at us. All right. Well, let's come back to it.
Yeah.
Hey everyone, I'm Matt Nicholson. I'm a sophomore engineering student at Northwestern University. I'm studying computer science and mathematical methods in the social sciences, which is a mouthful. Post-graduation, I'm really hope to work in kind of policy research, particularly the economics of education, because I recognize that being part of a FREM with great teachers like Mr. Grattoni, had an outstanding opportunity, and I would just like to research a little bit more about why that's possible in some cases, but not everywhere. So I'll have Roshan introduce himself as well.
Hello again. So I'm Roshan. I'm a sophomore here at the University of Illinois. I'm studying computer engineering, and so kind of this project helped me focus a little bit more on my interests. So kind of post-graduation, I want to go into a grad school and focus on the research there, but then after there, I want to go to an industry R&D kind of working on developing tools that improve people's lives. So it's kind of the aspect of this project that really helped me was kind of getting into that mode of research. Like if you have to do something, you have to begin at the basics and try to move from there.
Also, so not present right here is our third team member who worked on this, Jenny Yang. So I just, definitely worth mentioning that she was for sure a contributor to this project. So in terms of impact, this project and working in this course with Mathematica was kind of my first intro into a programming language, and I found it really cool, like what you could do and like the capabilities of Wolfram and that made me kind of want to explore that further, and that's definitely led to where I am today. Also, we got to pick a problem and kind of work out a solution, as Roshan mentioned, which is obviously something you do all the time in research.
So one of the most interesting aspects of our research was, I have a little picture here, was that actually the winter after we did it our junior year of high school. So the winter of our senior year of high school, we actually got to present this at a research symposium that was being held. So we got to expand beyond just the results of a demo, making it interactive, but kind of talk about what does it mean. So it was our project is based on this, we called it the spatial efficiency of a bifold door, something that we have in our homes, a simple closet door that's able to open and close. So we were trying to explore, one, the curve behind it, right? So like why would you choose a bifold door versus just a normal open and closed door? And then, but then we wanted to expand that into seeing like, okay, what would be the benefits of increasing the number of folds in a door, or how could you apply these mathematic things that we've learned during the year into things that we see in our daily lives. So we got the opportunity. We actually had if you can see it, it's kind of unclear, but we actually put a little bifold closet door in front of our presentation to make it a little bit more opening. But that was kind of the benefit. We got to go through the entire research process, but on a little smaller scale. But then we also got to show something that we were interested in, and proved that like we were able to expand this simple concept into something that could potentially mean something more. And
So yeah, now I guess we're gonna show off our project a little bit here. So here we have side by side a bifold door and just like typical double doors. And part of this project, as part of this project, excuse me, we went through and derived actually what this this curve over what this curve would be. So if you notice, it's kind of hard to see, and we'll wait for it to come back, I guess. Let's see. Okay. All right. Yeah, perfect. So what you can see here is that initially the bifold door, the curve that it sweeps out is determined by the hinge of the door, and then after a certain point, it stops being determined by the hinge, but rather the second door. So let's see that. Yeah. Oh, dang. Okay. All right.
Roshan, since this is the last slide, you theoretically, while he's talking, you might be able to go to close that completely, close out of Mathematica, download the CDF, and it might grow faster because we have so many demos all in one notebook. I think it's freaking out. I probably needed more RAM.
So we'll wait a sec for that to happen here.
It won't let you anymore. You have to download it. But you'd want to close out of yeah.
So I'll talk a little bit more about like why this was an interesting problem for us while we're waiting for this to go. So obviously, as college students, space comes at a premium. So we wanted to figure out a way to maximize our space. So it follows that we would study a problem like the efficiency of a bifold door. We're in a space where you don't have a whole lot of room. So as you can kind of see from that screenshot down there, that at the very bottom we have like a running count sort of the amount of area that the curve has swept out. And you can see that, or you will see very shortly, that the bifold doors are much more efficient in terms of saving space. And another thing that we found that Roshan alluded to is that if you were to continue with this and keep increasing the number of folds, it obviously gets more efficient. But then you have real world considerations like the thickness of a door and how practical is it for you to have a door has 20 folds in it. But yeah, okay, I think we're up and running.
Hey, Matt, remember when I told you we should be ready for technical difficulties?
Yeah,
I didn't know who it
remember.
was going to happen to, but I knew at least one of us.
Absolutely. All right, so let's start. Can we start without the curve? Yeah. All right. So we're just gonna sweep through this real fast. Side by side of doors, in case you don't know how doors work. So now we can throw in the curve here, and you see on the right you just have two circles. And then on the left, it starts off as a circle, and then the second half of it is an asteroid. Yes, asteroid. Sorry, excuse me. So now let's. The intersection point is there. Okay, yeah. So you can see that little black dot right there on both sides. That's the point that's actually getting swept out. So as the door opens and closes, the intersection point kind of travels for the bifold door from the hinge all the way down to the end of the door. So yeah, it's cool stuff, for sure. Do you want to talk about how we came up with this at all?
You could just click more really quickly and just,
All right.
and if someone wants to read your derivation, it's all there.
For sure.
They were very good at showing their work. I was very proud.
Yeah, so if you want to look through it, we did a parameterized version of this, so we were able to see like the actual direct results depending on where you are on the curve.
Yeah.
All right, and I think this is perfect timing for the Q&A if there's any questions about any of the individual projects or the idea for the project as a whole. Thank you, everybody, for attending.